So this different atomic level, molecular and orbital level description of what's going on in metals helps us to understand why metals are what they are, and it's also going to help us figure out why different metals have different properties. We're going to come back to this later, figuring out what makes a metal strong and weak and so on. We're going to be able to understand that in terms of the electrons and the band theory we just talked about. So far, we've only talked about lithium. We need to talk about other metals as well. So let's see how this all works out for some other metals. And so let's make not a very giant leap. Let's go to the next element on the periodic table, which is beryllium. And beryllium has the electron configuration 1s2, 2s2. And so if we make bands out by combining lots of beryllium atoms, so combine beryllium 1s orbitals and combine the 2s orbitals, and we have 2 electrons in the 1s orbital for each atom and 2 electrons in the 2s orbital for each atom, we might think immediately we're going to have a problem, because the 1s band will be filled, of course, just like it is in lithium. And what about the 2s band? This time we're sticking 2 electrons per atom in there. Really ought to be filled as well. And if it's filled, it's not going to conduct. So there's something odd. However, beryllium also has 2 p atomic orbitals. And even though there's no electrons in those p atomic orbitals, they're also close enough together that they overlap in this case, 3 atoms, 3 orbitals for each atom. And we wind up with a band of molecular orbitals generated by combining the p atomic orbitals as well. This is a 2p band. Now the 2p band doesn't have any electrons in it, but in an energy sense, remember this is energy going up. Energetically, the 2p and the 2s band overlap, which means some of the electrons can spill into the 2p band, and we wind up with one combined band. And this combined band can accommodate 8 electrons per atom. And of course, there's lots of empty orbitals, both bonding and anti-bonding, in this now combined band. So beryllium has lots of empty orbitals in the 2p band. They overlap with the 2s band. Therefore, beryllium is a metal. It's conducting, it has luster, it conducts electricity, and all that kind of stuff. The transition metals also have a band made by combining d-atomic orbitals. Let's jump straight to a larger element, titanium. Titanium has the electronic structure of an argon core plus 2 electrons in a 4s atomic orbital and 2 in a 3d atomic orbital. And so the 4s atomic orbitals will combine to make a 4s band, of course. And the 3d atomic orbitals will also combine to make a 3d band. And because remember, there are 5d orbitals, and so the 3d band can accommodate 10 electrons per atom. The 4s band can accommodate 2 electrons per atom. And the 3d band and the 4s band also overlap in energy. And so we wind up with a combined band which can accommodate 12 electrons per atom. And again, in the case of titanium, because we have 2 as formally associated with 4s and 2 associated with 3d, we have lots of empty orbitals up here. So of course titanium is a metal. Its electrons are polarizable, it conducts, it has luster, and so on and so forth. 12 electrons maximum, what that means is if we have 6 electrons, this combined band would be half filled, and the electrons would all be bonding. And that turns out to be rather important. Let's see how we can use that information to solve a problem in metals, see if we can understand something about the properties of metals this way. Let's compare chromium and copper. Chromium has a melting point of 1900 degrees C, very high obviously. Copper is much lower, it's almost half, I mean it's still very high, but it's almost half as, it's almost, the chromium is almost twice as large as that of copper. So how do we understand this? Let's look at the electron configurations. And so chromium is an argon core, 4s2, 3d4, and copper is an argon core, 4s2, 3d9. So we have different numbers of electrons, but it's going to be associated with the d band. So if we look at our band diagram again, chromium we have 3d4, 4s2, and in copper we have 3d9, 4s2, and so the bands are going to be filled differently. Remember, each band can accommodate 12 electrons per atom, and over here we have a total of 6 electrons. And so all of the electrons in chromium, they're all in bonding orbitals. However, in copper, we must have some electrons which are in antibonding orbitals within the band. So we have stronger overall bonding in copper because all the electrons are in bonding orbitals, stronger bonding that holds the atoms together tighter, that results in a higher melting point. We have to put more energy in to separate the atoms in copper and chromium. Chromium, however, has some electrons in antibonding orbitals. The overall bonding is weaker. That makes it easier to pull the electrons apart, to pull the atoms apart in copper, and that results in a lower melting point. So you can see, we can understand the physical properties of metals, things like how hard they are, and so physical properties on the basis of this band model, understanding what the electrons are doing at the electron atomic level. And we're going to use more of that in engineering when we return back to engineering context and figure out, well, what kind of metal would you use in a particular application, and how do you understand what to use on the basis of this kind of understanding?